Okay, good evening. This is Professor David J. De Los Reyes. Okay, my topic for this evening will be a very interesting topic, and this topic is one of the foundations of alternating current transformers, that is in the computation of the total power consumed by a three-phase load in terms of the line current and the line-to-line voltage, the line current and the line-to-line voltage of a balanced three-phase load. Okay, let's proceed. The subject matter for tonight will be a continuation of my long video format discussion or lectures, and this will now be alternating current machines, and this is now lesson number 43. We are running smooth. We are not yet finished with what they call this transformer. Okay, because the next thing after this we will be what they call this operating transformers and parallel. Okay, for tonight I will try to bring out the so-called derivation of the formula and how to compute for the total power consumed by a balanced three-phase load in terms of the line-to-line voltage and line current and power factor. This is a general equation. For as long as the load is balanced, it is three-phase, this should be the formula and how to compute for the total apparent, total true power. Okay, let's try to bring out a figure. For the meantime, let's just consider a Y-connected secondary, Y-connected. So this should be the first winding, second winding, third winding. This is the secondary portion, all right? Secondary. Okay. So if the connection on the secondary side is Y, and there is a balanced three-phase load connected at line number 1, line number 2, and line number 3. Three-phase load, this is balanced. So meaning to say, the value of the current IL1 is equal to IL2, and this should be equal to IL3. Actually, we do not need IL3, right? For the 2-watt-hour method, we just need the line current number 2 and number 1, and the line-to-line voltage number 1 and number 2. Okay, let's try to bring out the what I call this legend of this one. This is a wattmeter. Okay, so a wattmeter, there is the so-called current winding and voltage winding. The voltage winding measures the voltage across this, and the current winding measures IL1. For W2, wattmeter number 2, this is the current winding. The current passes through the current winding of wattmeter number 2 is IL2, and the voltage measured by the so-called wattmeter number 2 is actually BL2. The voltage between line number 1 and number 2 is BL2, meaning line-to-line voltage number 2. Okay. We let W1 be the reading of wattmeter number 1 and W2 will be the reading of wattmeter number 2. Okay, let's try to bring out the derivation. For wattmeter number 1, okay, it should be the product of voltage and current times power factor actually. This is a general equation. Meaning to say, if we try to take the reading of wattmeter number 1, we should take the product of BL1, IL1, and its power factor. Okay? The current passing through the current coil of wattmeter number 1 is IL1, and the voltage measured by the voltage coil of wattmeter number 1 is BL1. So to get the reading of this, take that current, multiply that by that voltage times the power factor, and that will be the reading of wattmeter number 1 in terms of watts. And so with wattmeter number 2, the current passing through the winding of wattmeter number 2 is IL2, and the voltage across its voltage coil is B subscript L2. Okay, so if we try to take the reading of this one, it should be BL2 times IL2 times its power factor, right? This is just the concept. It is this. Okay, I will try to reach this one so it will look nice. I have pronounced what is being written. Okay, let's try to take the reading of wattmeter number 1. Okay, I'll try to remove this one so it looks good, right? Okay, let's try to take the reading of wattmeter number 1. The voltage measured by the voltmeter portion of the wattmeter, because a voltmeter is a combination of an ammeter and a voltmeter. And to get its reading, you should multiply the reading of its voltmeter part, multiply it by the current reading by the ammeter part times its power factor. So actually, wattmeter number 1 will be BL1, the voltage across this. The current passing through it is IL1, right? And the power factor is actually, we have, I give you this one on the open delta or delta connection already. It's the cosine of 30 degrees plus theta. This one actually came from the so-called vector diagram, right? In which the voltage is this one, and the current is this, right? There is the so-called 30 degrees minus theta, and the other one is 30 degrees plus theta. Okay? Okay, I will try to rest. Okay? So the power factor of wattmeter number 1 will be this. Okay? This one was actually derived by bringing out the vector diagram of the voltages and current. Okay? It should be cosine of 30 degrees minus theta. So if we try to expand this one, okay, but before we expand, for a balanced three-phase load, so we didn't always write the subscript 1. I just place voltage across line number 1. It will be just simply BL without the subscript 1. And IL1 will just be simply IL. Okay? To simplify the writing of the subscripts. So instead of writing BL1, I just put BL, the line-to-line voltage. And the current passing through line number 1 is just simply IL. No more subscript. Why no more subscript? Because for a balanced load, the current line current number 1 is just simply IL, and current number 2 is simply IL. No more subscript. This is balance, right? So we forget the subscript already, and this will be simply B sub L, the line-to-line voltage. And this will be the line-to-line voltage without the subscript 2. Because the voltage across this is equal to this, so we don't need any subscript. So if this is BL, this should be BL. And if this is IL, this should also be IL. So to simplify the writing of the subscript, we just place BL1 to be equal to BL, and IL1 be equal to IL. So this will now be BL times IL. And if we try to expand this one, this is a part of the so-called expansion of a cosine of a double angle. Okay, double angle. The angle inside is just 30 degrees minus theta. That's trigonometry. 30 years ago, I could still memorize this one, the cosine of a double angle. It should be cosine, cosine, sine, and if this is minus, this should be plus. Okay? Cosine of the first angle is 30. The first angle is 30 degrees. Second angle is 30 theta, right? Cosine, cosine, sine, sine. If this is minus, this should be plus. Okay? 30 years ago, I still remember it. Right? Cosine of 30 degrees is 0.866 cosine of theta. Sine of 30 is 0.5 sine of theta, close quantity. This is multiplied by BL and IL without the subscript 1 and 2 already. Because 1 and 2 are actually the same. So if we see line-to-line voltage, it will be equal to BL1, BL2, BL3, or just simply BL. We call this equation number 1. Alright? For the reading of wattmeter number 2, it should be the voltage reading, the product of the voltage passing through its voltage coil times the current passing through it. It will still be BL2, IL2, cosine of. For the second one, we derive this cosine of 30 degrees plus theta. This actually emanates also from the vector diagram. This one. Right? And to simplify the writing of the subscript, again, I will write BL2 as just simply BL and IL2 as just simply IL because the load is balanced. Okay? These are all IL, same value. Voltage across this equal to the voltage across this equal to the voltage across this. No more subscript. So, the expansion of this one will now just be simply no more subscript, okay? It's balanced, BL, IL. And the expansion of this, it will be same as the expansion of the first one, but if this is plus, this should be minus. You got it? The first one, it's minus, so this should be plus, right? If this is plus, the expansion should be minus. That's the difference, okay? So if we try to expand, it will be cosine, cosine, sine, sine. If this is plus, this minus. 30 years ago, I still memorize it, right? So cosine of 30 degrees, cosine of theta, minus sine of 30 degrees, sine of theta. Cosine of 30 is 0.866 cosine theta. Sine of 30 is minus 0.5 sine of theta. It's the same as this one, but this is minus because this was plus. Okay? We call this equation number 2. Okay? Then let's try to add equation number 1 and number 2. So the left hand side, W1 plus W2, okay, the left hand side, equal to. If you try to notice it, this portion here, okay, I will write this in blue. This one. And this one. They are the same, right? This is plus, this is plus. So it will be a common factor BLIL. This is similar to this one, so they will add up. It will be times 2 inside. So I place a multiplier to here times 0.866 cosine of theta. Okay, so I add this one already. For the second part, this is plus 0.5 sine of theta. This is minus 0.5 sine of theta. We are adding it, right? So actually this one here, cancel with this. So this is now plus 0, close bracket, okay? So no more sine of theta. Why no more sine of theta? Because this is plus and this is minus, they cancel out. So actually it's just something like this, okay? And we let P with the subscript capital letter T, meaning the total true power will be equal to the reading of wattmeter number 1 plus the reading of wattmeter number 2. Instead of writing W1, W2, we'll just place a capital letter P with the subscript T, meaning total true power. So for a balanced three-phase load, okay, P total will be equal to 2 times 0.866 is 1.732 times B sub L times I sub L times cosine of theta. But what is 1.732? It is square root of 3. Right? So in general now, for a balanced three-phase load, okay, the total true power will be equal to a factor of square root of 3 times the product of the line-to-line voltage times the line current times power factor, in which power factor is actually equal to cosine of theta. So this is now the general equation on how to compute for the total true power of a balanced three-phase load, okay, in terms of the line-to-line voltage and the line current. Okay, so this is a general formula. Okay, that's it. So if you try to Google what you call this, the total true power consumption of balanced three-phase load, there is a factor of square root of 3 there. And that square root of 3 actually emanates if the load is actually a balanced three-phase load. It should be square root of 3. It is not times 3. It is square root of 3. Okay, that's it, guys. So that's the so-called derivation of the total true power consumption of a balanced three-phase load in terms of the line currents and the line-to-line voltages. Okay, this is Professor David J. De Los Rios. Good evening from Los Angeles.